Hello, everyone. I welcome you to the 44th episode of the Net Zero Energy Building Knowledge Series. This is the platform for the industry to share their expertise, projects, products, technologies, research, and ideas to fuel discussion on energy efficiency and grow engagements in net zero energy buildings in India. I'm Anval, working as a green building analyst at Environmental Design Solutions, and I shall be the session moderator today. It is a clear and cool morning here at Nainital, where I'm working from home. Hope your day has started off well. The webinar series is executed under the MATRI program supported by the USAID. MATRI is the acronym for Market Integration and Transformation for Energy Efficiency. MATRI supports the three main program areas where energy efficiency, sustainable cooling, and training and consumer engagements. The program works in partnership with several organizations such as Energy Efficiency Services Limited, Bureau of Energy Efficiency, and others to implement various initiatives. The market transformation approach includes creating business opportunities for the private sector, scale up of potential initiatives, and enabling policies as well as providing trainees for the net zero energy buildings. MATRI is supporting efforts moving towards a super efficient and net zero energy targets for buildings in India. The Net Zero Energy Building Knowledge Portal is a one-step site for information on NZEBs. You may explore this further on the website .nzeb.in. In today's webinar, we are going to learn about the future of carbon neutral design. With growing demands to address climate change, we need to go beyond just addressing energy use in our individual building. Taking an integrated approach to address both energy and carbon emissions through the entire life cycle of a building. I take this opportunity to mention that under the MATRI program, we are working on grid integrative net zero energy buildings to spread awareness for accelerating the efforts toward decarbonizing, decentralizing, and digitalizing the grid of the future for India. We will share more information on it very soon. Let's now learn about carbon neutrality from Shruti, the expert speaker for today's session. Shruti is joining us from San Francisco, where the time zone is just the opposite. It's 9:30 p.m. over there. Welcome to the webinar, Shruti.
Thank you very much. Very happy to be here.
We are also. Shruti is an award-winning sustainability consultant with 15 years of experience in advancing sustainability within the built environment. She has led multiple highly ambitious and complex projects from laboratories, museums to master plans. Her work on the sustainability in the built environment has been presented at several leading industry conferences. Shruti combines technical competency and creativity across multiple disciplines, architecture, engineering, and master planning, and has developed deep expertise in passive systems, energy optimization, and carbon management. Welcome to the webinar, Shruti. We look forward to learn the process that can be used by the project teams to make the carbon smart design. There will also be a live question and answer at the end of the webinar. If you have any questions during the presentation, please type them into the question box. So now I hand it over to Shruti.
All right, fantastic. Thank you very much for the introduction. And let me share my screen. Hold on for 1 second. Okay, Are you able to see my screen now?
Yes.
Okay, fantastic. Oops. I'm gonna do it this way and get into a presentation mode. All right. So thank you everyone for attending this webinar with me, and thank you for inviting me to speak on this topic, which is very close to my heart. Um, I've been introduced already, but just like a brief introduction for myself. I'm born and raised in India and migrated to United States several years ago now. My professional experience has been in North America. However, in this presentation, I hope I share with you my experience in designing high performance buildings and where the future of carbon neutrality is in the context of North America. But then I also hope to share with you some of the parallels that I see around the sustainability issues and drivers that may be relevant for India as well. So thank you again for attending this webinar with me. Okay. So a little bit about my company. I work for a company called Atelier 10. We are a progressive group of environmental designers who are committed to making a positive change in the built environment. We are a team of architects and engineers and environmental policy experts and lighting designers all coming together and lending our own perspectives on how to our practice principle is based on the fact that we want our buildings, our architecture to do more, systems to do less, and be pragmatic in the way we design our buildings. We offer our services through mostly through consulting and under the umbrella of what we call as the environmental design, which consists of many, many things listed here. And we have 11 offices around the world. We are quite global in that way, and we've been around since 1990. We run our company quite collaboratively and draw from all the international experience and climate zone and regional experience that we have around the world. I just put this slide together to give you some sense of where I'm coming from and what my perspective might be. So carbon neutrality has been a hot topic, at least in my world. What we have been seeing and what we have been actively doing through our work is looking at carbon neutrality on a variety of building types and scales. So what you see here is a project that I'm actually going to present quite a bit in detail, the California College of Arts expansion project, which is a very fun project here located in San Francisco. It is a smaller project that deals with carbon neutrality in a much more meaningful way than we've done before. And it also has a cool hydrogen story. So I'll get to that in a little while. We've also dealt with carbon neutrality on campus scales. We recently completed the UC Merced 2020 campus, which consisted of 11 buildings that were built under 5 years, designed and built under 5 years. And they're all very high performance buildings. And the goal of the whole campus is to achieve carbon neutrality. The other one that I wanted to show here or include in this list is a really high performance project called the Jewel Changi Airport in Singapore. And this is one of those projects which is highly Instagrammable. So you'll see lots of pictures on the internet about this with a waterfall in the middle of the building. Again, a very different type of approach here when you're designing for plants indoor in a subtropical climate, but designing high performance buildings in that context. Here you also see the Google Bayview and Charleston East campus, which is a Google tech headquarters here in the Silicon Valley. And these projects are really asking us to look at the built environment quite differently in a way that focuses on environmental sustainability, but also health and wellness, and definitely, again, pushing for carbon neutrality on a much larger scale. There are more types of projects. These are close to high-rise projects. 7 carbon neutral towers in San Jose, which is close to San Francisco here. And here the idea is to get to carbon neutrality in a dense urban setting with very limited area for any PVs or any on-site renewable energy generation. So it is a different type of challenge in that way. And then the Comcast Technology Center here is also one of our highly performative project where it's a high-rise building in a cold climate, achieving really high performance goals. So again, just giving you a sense of the range of projects that we're looking at to move the needle and make progress here. And I have cherry picked one of them to present today. So before we get into the particulars of the project and even the particulars of this topic today, why carbon? Why are we talking about this? And most of you may already be aware of this, but really a couple of years ago in 2018 now, so that's not a couple of years ago, but a few years ago, the Intergovernmental Panel on Climate Change, the IPCC, released a new report. And the understanding before the 2018 report came out was that the critical threshold for acceptable climate change, global warming, is 2 degrees Celsius. That was considered to be a worldwide accepted threshold. And then in 2018, this report came out, which basically said that the scientists warned us that, in fact, we need to be under 1.5 degrees threshold, and that we are likely to start seeing effects of global warming as early as between 2030 to 2052. And just thinking of that for a moment, 2030 is like literally 9 years from now. So that really prompted us to think about how we are talking about carbon and what actions we're taking right now in this decade to make a meaningful impact on the built environment. And speaking about carbon emissions and climate change, inherently, climate change is unequal. There are certain countries who have contributed in the past and still do in a much more significant way to the global carbon emissions than others. And yet, you know, the effects of climate change are spread worldwide and are unfortunately are being hit onto the countries that may be least prepared to tackle the effects of climate change. And here is a map showing the range of impact from yellow being the least impact to the purple and the dark colors being the most severe impacts. And you can start seeing here, this is showing the water impacts, which basically includes any sort of like water stress or drought intensity or non-renewable groundwater issues. And we're looking at a 2-degree scenario here. The next one, we're looking at the energy impacts, and this, you know, encompasses clean cooking access and heat events and cooling degree days, and also, you know, hydroclimate risk to power plants on how power will be delivered to cities and to houses. And then the land impacts, which, you know, covers crop yield change and habitat degradation and agriculture, water stress, and nitrate leakage. So all these issues, as you can see, are very much relevant, and no matter the cause of climate change, whatever it is, I think it falls onto everyone to at least prepare for the effects of climate change. And I find this like very interesting. I think like India is on a cusp of a major revolution here, which is the opportunity of this decade. And think about this statement for just a moment, that 70% of India's 2030 urban infrastructure is yet to be built. And so we're talking about from now until 2030. And India has signed up for the Paris Agreement, which commits India to reduce carbon emissions to by 30 to 35% below 2005 levels in this decade by 2030. It also has committed in a non-committal way to having 40% renewable energy supply in the power mix by 2030. So this decade seems like there's a lot of things going on that are especially in architects and designers' control, and that'll tell how the future of these buildings that are being built, that are being conceptualized right now, and that'll be built in the next decade, and that will be occupied in the next 50 to 70 years, how those contribute towards climate change. But really, for India, I feel like, and also in several parts of the world also, it's not just about climate change. It's not just about reducing greenhouse gas emissions. That is, of course, the priority of how the buildings can reduce carbon emissions at all life stages. And we'll talk a little bit about this, all life stages, in more detail. But then it is also about energy and water security, of how do we design strategies and how do we design the built environment to have reliable access to energy and water all year round. And at the same time, how do we also get the buildings ready to operate without water and power, at least at certain times of the day. And then, building in resiliency on how do we make the buildings ready to combat the effects of climate change. And the issues sort of vary depending on which place you're looking at. So how do we identify those issues? So for me, climate change and reducing greenhouse gas emissions and designing for carbon neutrality is considering all these elements and hopefully coming up with strategies that address all of them. And just to again, like putting it back onto my experience and what we deal with on a day-to-day basis. Here's, in the United States, it's no different. San Francisco, California, sorry, has committed to having 60% of its electricity be carbon-free by 2030. So similar targets. And then also has committed to have all electricity be renewable by 2045. New York is slightly ahead here, very competitive, 100% renewable electricity by 2040 and 70% renewable electricity by 2030. So again, we are seeing a similar kind of movement going here in the United States, this decade being extremely important. And I'll talk a little bit about the time value of carbon here as well. In addition to that, we are also seeing through codes and standards a shift from not just requiring renewable energy be embedded into reducing the operational greenhouse gas emissions of the building. We are also seeing that state agencies are asking to consider embodied carbon emissions of materials into the buildings, and that therefore is becoming more of a state-driven conversation now than than private developers or owners individually coming up with those targets, which is a great thing. So putting all of this together, decarbonization in my mind is more than just designing low energy buildings. Decarbonization of the built environment, we as designers have a lot to influence. And here's just a list of all the things that, I definitely wish and hope and try to address on as many projects as possible, from energy conservation to where my energy is coming from, where my power is coming from, and how do I make sure that it is carbon-free 24/7, the embodied carbon of materials, and then the boundary can be expanded very well, and it is a very meaningful impact if we do so, including refrigerants that go into our buildings, whether it is through air conditioning or whether it is through processes, waste that is coming out of our buildings, whether that is through consideration of circular economies and deconstruction of materials and assemblies, and operational waste as well as water. Energy consumes water and water consumes energy. So there's an energy water nexus there. Transportation, the energy required and the carbon emitted as a result of people going back and forth. And then the piece that can meaningfully be a positive element in all of this, while everything else is consuming and producing carbon emissions, landscape carbon sequestration. So we'll talk a little bit about that as well. So in this presentation, I have mostly focused on energy sources and embodied carbon of materials, just because otherwise it'll be a very, very lengthy topic, but happy to have more discussions around any other topics as well. So let's dive right into embodied carbon. So you may already know what embodied carbon is, but for those of you who may be new to this, the idea here is to look at the materials that get built into the building through their entire life cycle. So let's take a new construction. Materials that get built into the buildings have to be extracted first, and then they have to be assembled and manufactured and then transported, and then they get put into your buildings. Through the life of the building, there are renovations that are happening in the building. So all of those, the energy associated with those renovations. And at the end of life, there's the disposal. So all these stages within the life cycle of building products emit CO2 emissions and are responsible for a lot of carbon emissions. So you may have seen this also, that buildings are about 40% of global CO2 emissions. And, you know, until now, there was this other stat floating around, which was that building materials and construction is about 11% of that, building operations is 28%. So this is more important. How do we sort of make our buildings energy efficient? And you know, there is a very important distinction here between operational energy use or operational carbon emissions and embodied carbon emissions, and which is the time value of carbon. Again, talking about this decade, talking about what we can do right now and the impact of those decisions on the environment right now. So what this graph is showing us is total carbon emissions of global new construction from 2020 to 2050. And what we are seeing here in yellow is the embodied carbon emissions. So buildings are getting built and embodied carbon emissions are being created as a result. And then, you know, the blue is operational carbon, which is that buildings are getting built and they start emitting carbon, and then they do that the next year and the next year, and then that accumulates over time. And when we start thinking about, you know, the embodied carbon of materials, therefore, for a 30-year or a 40-year life period, then they are about 50-50%. So in the end, you know, both of them, the operational and the embodied carbon, are about equal. But if we think about it, the control that we have in our hands right now is embodied carbon, the material choices that we are making. And that is the carbon emitted right now. And that is resulting in the global warming that is happening right now. So that is, in a way, the most precious carbon that is being emitted right now, because once that carbon is emitted, you can't take it back. So therefore, embodied carbon emissions, what is happening right now, is in a way more important than even operational carbon, which sort of like accumulates over time. And as electricity gets more and more renewable, who knows, that blue trajectory might actually flatten out a little bit. So, you know, we started doing this recently on projects where we routinely do LCAs, which are a short form of life cycle analysis, which is basically taking all the materials in the building and quantifying them, and then figuring out what is the CO2 emissions associated with each of those materials, and then giving it like a number on in terms of what the overall building carbon emissions, embodied carbon emissions are. And you know, it was very usual to look at a 60-year life period for a building, and then compare the embodied carbon emissions of a building to the operational carbon emissions, and it always looked like a smaller fraction. But then if we start looking at it, instead of 60 years, and if we start looking at it for 20 years, then we quickly see how important embodied carbon is in comparison to operational carbon also. So many exciting things have happened in the last 5 or so years in the world of embodied carbon life cycle standards. And I tell you, like 15, 17 years ago, in school when I was doing my master's, we tried to do an LCA of a product, and there were no resources, there were no standards. Information was not out there. The suppliers, the manufacturers that we were calling couldn't understand what we were talking about. The world was just not there. And some smart people have put together their brains in these last few years and really decided that this needs to change and come up with processes so that architects and designers can do apples to apples comparisons between products and make better decisions for their buildings. So as a result, now there's a process which is defined in terms of stages. And here's the whole building life cycle, and it is divided into a product stage, a construction process stage, use, end of life stage. And then there is a very systematic way of calculating the embodied carbon associated within all of these stages so that you can compare one system to the other, you can compare one product to the other, you can compare a building to the other and make wise decisions on your project. So very thankful that that has happened in the last few years. And this area is also quite evolving in a way. For those of you who care about LEED, LEED cares about, if this is like a simple section of a building just for diagramming it. And what this is showing is that for LEED typically will only look at structure and enclosure. We believe, and we always try to include more than what LEED asks us to do, which is the complete building, and I'll show you some examples of that as well on what happens when you include interiors and systems, building systems, whether they are lighting, HVAC systems, IT systems, all of those fun things that make the building work, all of those together. And then, again, there's this opportunity to push the boundary here and include a complete project, which would include your site, which is the paving and your grading and excavation, all of those elements, as well as landscape. So those of you who care about benchmarking, LEED has started recognizing whole building life cycle assessment, and there are up to 3 points available for it. And then also ILFI zero carbon certification, if you are interested in that, also gives projects a lot of credits if you're tackling some of these challenges. And the way we start looking at some of these issues in early design, which, oftentimes, we start on a project and all this information isn't available. We don't exactly know how all the materials are going to get put together. And it can we don't want to get caught into this like analysis paralysis type of a situation. And so, in early stages, we find it to be perfectly all right to do a material level comparison. So for example, here you're seeing a comparison of different types of insulations, and which may be less relevant in the Indian context in some cities, but more relevant in others. And so is the case here in the United States as well. So insulation, this type of comparison can tell you for 1 inch of or R1 insulative thickness, what is the embodied carbon impact of a material. And those comparisons can still be made to make some early stage decisions. Similarly, here what you're seeing is some shading systems, and here you're seeing some facade systems. So each of these lines is a system, and higher the line, it means more the global warming potential of that product. And so you can begin to layer these on top of each other and see which one is the highest or the lowest, and make decisions along those lines. So here we are comparing a fabric sun control system to a metal sun control system to a louvered metal sun control system. So these two are both metal, but they are designed in a slightly different way. This is fabric, so clearly it is going to have a lower global warming potential. The next one that I wanted to just share here with this group was we found that, concrete, our dear friend concrete, has a lot of potential to reduce its carbon emissions. And in fact, it can be one of the biggest things that you can do on your project. And here's an example of a structural system LCA we did for a local county building here in the Bay Area with Studio Gang Architects. And basically what these colors here are showing different concrete packages. So, the concrete mixes are not going to be same for all the applications in the building. So this is showing the different packages, the concrete mixes that were present in that project. And then for each of those mixes, we worked with the structural engineers as well as the manufacturers and the suppliers to come up with the right cement replacement values or other aggregate replacements and whatnot. So basically the mix design for each of these. And achieved pretty good reductions, 50% to in some cases it is lower than that, overall reductions just through optimizing concrete. So I know that that is quite business as usual in India, but again, like quantifying that and figuring out where a big dent can be made can really move the needle on the project. And then here's again like a tool on how do you sort of like process this data when you're working with the design team. So this is basically telling you this is basically different mixes that we are looking at, and this is telling you for a certain mix design, if you want to get to an overall building reduction of 20%, how can you combine different mixes to get to that target. So this is sort of like doing a parametric analysis so that the architects could like choose their path to getting to that target. I talked about interiors a little bit, so I'll mention this. For interiors optimization, we've also worked quite a bit on how impactful interiors can be, and this is for one of the tech headquarters project here in the Silicon Valley. And we found that just isolating interiors and looking at interior products, which often get neglected, like interior paints and carpet tile and insulation and gypsum board and tile flooring, all these elements put together, we found that not sort of like going out of our way, just making some wise decisions and just like literally like reading information about these products and making some wise decisions and like tracking it gave us about 10% savings in just the interiors GWP reduction. So the UC Merced project allowed us to basically do an embodied carbon calculation and optimization across several buildings at the same time, which was great. And what we learned from that is that here in the United States, which may or may not be exactly applicable in India, is that concrete can be optimized up to 30%. If we're looking at a steel building, which often happens here in the US, it's a similar range. And then timber is a big deal these days. And sourcing timber is a very important criteria there. So just selecting timber as a choice of material isn't necessarily going to give you any different reduction in carbon emissions, but sourcing that timber correctly so that carbon can be sequestered, which is the big differentiator, can really move the needle and get you up to 70% savings. I cannot complete a discussion around LCA and embodied carbon emissions of buildings without talking about existing buildings and adaptive reuse. So here's a case where we did an analysis to convince and to show the owners of this building. In this case, it was Cal State LA institution, and the idea here was to quantify for them the effect of just reusing the building. So just reusing the building without having to demolish it and build whole new. Just that one decision alone allows the project to save 30% embodied carbon emissions, which is pretty cool. And then, you know, you can optimize that further to achieve up to 50%. Last year, and then I want to move on to another fun topic before I present the case study, is the Pathfinder tool, which is we partnered with CMG Landscape Architects, who are a local landscape architecture firm here in the Bay Area. And the idea here was that, hey, for projects that have a big landscape component or an open space component, that's the only element of the project that allows you to actually sequester carbon and be climate positive. And here's a tool. This is actually freely available, so feel free to note the path and try it out on your project. But this is a way to include landscape into this conversation and push the boundary on planting design and planting selection and actually getting to net positive carbon. So the next one, I'm going to just change gears a little bit and talk about grid carbon, which is the carbon associated with operating the buildings. And in these last few years, we've done some deep thinking, and we are really changing the way we think about greenhouse gas emissions and energy use. And I'm going to tell you why. And you know, the fundamental process of designing buildings to reduce its carbon emissions, operational carbon emissions, is still the same. And our vernacular architecture in India and the critical regionalism that we see all over India is fantastic. It's the best thing that we can learn from traditional Indian architecture, which is the passive systems. Now, how that gets applied to urban scenarios and dense urban locations is, and also taller buildings, is something that is interesting. And that's where I feel like active systems and plant design and integrating renewable energy, that all those elements come into picture. So we believe that any good design should start with a really robust passive scheme, and that's the way to go. And then, you know, optimize your building using active systems and using high performance plants, integrate renewable energy as much as possible, then look at offsetting on your own site, and then integrate landscape to make it a carbon positive building if possible. Now, one thing that we are so glad has happened, I kid you not, for the last several years, we kept on pondering when any net zero definitions were thrown around on why are we not talking about carbon? Don't we care about climate change and carbon emissions? Why are we not talking about carbon? Why are we talking about energy? So here's the graphic that we had produced, I don't know, at least a decade ago, if not more, to explain the differences, which was when we're talking about site, if this is your building, we are measuring the energy right here at the meter. When we are talking about energy cost, we are talking about, again, the energy measured at the meter, and here the dollar value or the rupees value that is being paid at the meter. California had its own definition, which was source energy, which was basically like somehow measuring it here, but then also like factoring in some transmission losses and whatnot. And they were like trying to get to carbon emissions, but not quite. And then straight up carbon emissions. And we are so glad that we are finally talking about carbon emissions, which is what we should be caring about as architects and designers, because our buildings are not islands in most cases. Some of them are. But most of them are grid-connected buildings, and our buildings have a large effect on not just what goes within the building, but also on the larger grid. So not all energy is created equally. So why did we not like using energy use as a proxy for carbon emissions? And here's a map showing for a year, this is like a average day And this is looking at the green is when carbon emissions are pretty low. Sorry, this is energy use. Energy use is pretty low. Red is when energy use is pretty high. Yellow is somewhere in between. So this is basically saying that in the summer season, which is June through September here in California, buildings consume a lot of cooling energy. It is high. At night, no one is occupying the buildings. It's all green. Now, the cost structures traditionally reflect this same pattern. So you see, when you use energy more, you get penalized for it. You have to pay more for it. That makes sense. However, if you look at carbon emissions, which is this one, you'll see that carbon emissions have no correlation with these two whatsoever. So yes, reducing energy use within your buildings is a great idea. Knowing when your building uses energy is a great idea. And saving money while doing so is also a great idea. But it may not have the same effect that you thought it has on carbon emissions. And the reason for that is that carbon emissions of your building is totally dependent on how the grid is operated. It has less to do with what your buildings are demanding and more to do with how the grid is operated. So grid emissions vary by time. So here's a projection for India. So the blue line here is like a base case for 2018. So carbon emissions intensity for a typical day for 2018. So this is sort of like showing that it doesn't really matter when you're, using energy, because it is pretty flat. So, you invest in energy efficiency, you reduce your energy use of the building, and your carbon emissions will go lower, which makes sense for a grid that was coal-based. Now think about it. Now our grid is evolving. Think about that Paris Agreement and some of the commitments that India has made and the US has made and all other countries have made to increase the renewable energy penetration into your grid, which means that as you start putting more solar, more wind into your power mix, your energy profile starts looking something like this. So this is an IEA carbon emission projection for India, and this is showing two different scenarios. The orange is showing a medium scenario where the grid is being modernized and renewables are being put into the power mix, but it is still sort of okay. And this is like really aggressive, high performance, so it's really low carbon. But notice the difference in the shape. So here is the dirty time on the grid. Using electricity at this time is going to cause more carbon emissions. Here is when it is a clean time on the grid. So using electricity at this time is going to cause fewer carbon emissions. And you know what? So this, what I showed you, is a projection for 2040 for India. We experienced something like almost identical in 2015 in California. For the last 15 or 20 years, there have been like several incentives in California to add solar, both on the utility side as well as directly onto the buildings. And what that did was, so the blue line here was the actual energy use, or energy use on the grid. And it used to be, again, quite flat. It did sort of like peak in the evening, but it used to be pretty much flat during the daytime. And then as more and more renewables got added onto the grid, it started dipping. And that got famously named as the duck curve, because it looks like a duck. And the belly of the duck is basically where it dips. And that like changes completely our thinking around where we should be focusing on if we are trying to reduce the carbon emissions of our building. And how can we control the carbon emissions so that we can take advantage of the times when there's a lot of renewable energy in the grid, and how can we shift the load from of the building from 1 hour to the other. So the old way was to look at the energy use of your building and then figure out your greenhouse gas emissions factor, which was sort of, either an average number, sometimes like an annual average number, maybe from your local utility or from a state average, and then multiply those two and you have your greenhouse gas emissions. Not accurate anymore. So the new way is basically looking at the energy use, which is what you do through your energy models, through your simulations, but then looking at it at different times. So factoring in the time of use in that. And then looking at the greenhouse gas emissions conversion factors on a marginal basis. And I'll get to that a little bit. So integrating that time of use is an important consideration now. And to understand why this is really important is these are the balancing authorities, how the grids are laid out in the United States. And if you follow US news in any shape or form, there was a major storm and a grid incident in Texas, which is right here. And this grid region, which is this gray blob here, isn't connected to other grid regions, and that caused a lot of problems. Traditionally, all these grid regions are basically electrical networks that are all interconnected, and they exchange electrons, and they're balanced in a way so that we get electricity. And here's how this looks for India. There's the western region, the northern region, northeastern, eastern, and southern region. And so far I could tell is that the eastern region pretty much sort of like connects to all of them, and it also has excess power that is being produced and therefore sort of like feeds into these. So I know this gets a little bit too technical, but basically, if we are serious about carbon neutrality, this is what we got to understand. This is what we got to understand on how these grid regions are connected to each other, where those electrons are coming from, and what is going on in this blue region. I'm just like hovering over here because I'm from Pune. But essentially, what is going on in your grid region, and how is electricity being exchanged between regions? So the average hourly emissions basically look at the power mix at your utility, whether it is a mix of nuclear and oil and solar and gas, and then average them together, and that's your average hourly emissions. Marginal emissions is really what we care about, and that's the true metric that we should be using, which is, there are several plants that the grid is extracting electricity from, but for the new load that you as a designer are helping design and is getting built, for that new load, there is a plant that has to be turned on as a result of the new load. And the emissions that your building is responsible, therefore, is the emissions associated with that plant, and that traditionally is called, or in the technical context, which is called the marginal hourly emission. So that is the real effect of your building, your building's carbon emissions. So the gist of all of this is buildings are not islands. They are a connected resource in a very large network. And beyond buildings or good building design, which includes load reduction and demand response and all the good things that we have learned to do in building high performance buildings. In addition to that, there is the grid connection and the fuel mix that needs to be factored in to be able to meaningfully reduce carbon emissions of our buildings. So if you are interested in more on this, we have a white paper written by my colleagues, The Future of Carbon Neutral Design. It can be downloaded from our website. Here's the link. And if you have more questions, very happy to talk to you about any of those. So I'm going to spend the last few minutes here. I know we're going to run out of time very quickly, almost like showing you the application of some of these concepts. So designing for carbon neutral, I'm going to present the California College of Arts project with Studio Gang. This is San Francisco right here, and California College of Arts is a academic building that you see here. And if you again are familiar with the geography here, they have a campus in San Francisco. They also had a campus in Oakland, which is just across this bridge here. And they decided a few years ago that they want to consolidate it all together in San Francisco. So that's what they planned on doing. And then we got this project and we were like, oh, it's an academic building and, high performance academic building. I think net zero energy was how it was labeled at the beginning, I believe, first. And we were like, oh, we have this down. This is like totally, we can like completely do it. We know how to do it. No problem. And, we started working on it. And it consists of this big podium here and these two buildings, a nice open space. We started with all those passive concepts that we were talking about. Like, let's define the thermal and the visual experience so that we know where we can utilize natural ventilation and passive design and shading and all these great lighting and conditioning controls, and identifying where a variety would be okay. Then we developed several concepts around interior and exterior shading, passive cooling, night flush, thermal mass, natural ventilation, daylight, all the good stuff. Had some holes into this large plinth to move the air and make natural ventilation work. And then reality hit, which was that, yes, we can make academic building really high performance and get its energy use down as much as possible, no problem at all. However, this is an arts building and has what they call as the makerspace. So the makerspace is the space where they do all sorts of cool stuff. They blow glass, they create sculptures, or like make all sorts of art. It is a very energy intensive space. And you can't just take away electricity because you want to make it energy efficient. That is the process. That is the purpose of this building. So the makerspace equipment, it is, you can sort of like think of it as like some process load or some industrial load that cannot be taken away. And yet this building had to be a carbon neutral building, as we learned more. So, we again like ran the best of the analysis. These are some of the natural ventilation studies that we ran to identify the red dots here show when natural ventilation couldn't work. And then how do you sort of like start tweaking the building to shade it more, to open it more, to design it well, so that you can use natural ventilation more and more. And, we were trying to like squeeze everything out of all the strategies as we could out of this project and into the project. And in the end, again, what it came down to is that, yes, here's the energy distribution of the academic building, and we can get it really down and minimize it to some lighting, some fans and plug loads. But what about all of this? We really can't control this. So how do we deal with that? Put PVs onto the building, and we did that. So this is the actual buildings here, and we looked at the roof of the neighboring building and put PVs all across that roof and our roof and maximized it, and yet we couldn't reach carbon neutrality. So that's when we, started thinking on how can we utilize the PVs that we have and some of these natural ventilation passive design strategies that we have to our advantage, and really understand how carbon is emitted throughout the year, and how the grid is operated so that we can shift it around. So basically what we did as a result was, we have this efficient building, we have PVs on the roof, we added batteries in and essentially created a microgrid out of this. So basically what that means is that we have control over where the electrons are flowing. We can push the electrons from the PV system into our building. We can push it to a battery, or we can push it back to the grid, depending on what is the need of the building. And then what is that based on? That is based on the grid greenhouse gas emissions. So looking at what the grid is doing, if the grid is really dirty, it is time to use PV. If we can project and predict that the grid is going to be dirty tomorrow, then we produce PV, we produce some excess and put it into a battery so that we can use that during the time when the grid is really dirty. When the grid is really clean, why use PVs then? Let's use the grid electricity. So doing this balancing, so that's the controller logic that we developed to basically maximize both PV array production, the battery charging and discharging, as well as how the passive systems were working together with these. And that was basically the concept behind getting to net zero, getting to carbon neutrality on this project. And here are some of the graphs that are showing on how shifting that load from PVs onto the batteries allowed us to save carbon emissions, especially during the times when the grid is really dirty. One of the cool things that we also looked at, and this was mostly came from the ownership, which was to look at renewable hydrogen as a possibility. So here the idea is that instead of we would have the PV that we had, but in addition to that, if we dedicate some on-site PVs to produce electricity that then can be used through electrolysis to create renewable hydrogen, and that renewable hydrogen then gets pumped into it powers a fuel cell, and the fuel cell we can use whenever we want. So we are not tied to the carbon emissions associated with the grid, and we are essentially creating a fuel on site that is completely renewable. This was an exploration, and if you sort of Google hydrogen microgrid or hydrogen economy, you'll see that there's tons of research and tons of money that is being put into developing these products. We believe that maybe a packaged product like this will become available in the future. Right now, the technology isn't there, but we do think that hydrogen is going to have a pretty significant part in our solution to get to carbon neutrality for the bigger built environment. And that is pretty much it. My apologies, I'm a minute over here, but I hope that is okay. And I'll stop sharing for a bit. Are people still there?
Yes, yes.
I was for a minute. I'm like, okay, what happened?
Okay. Thank you for sharing your case studies, ideas, and the strategies which can enable a shift from the net zero energy building to the carbon neutral buildings. We should also aim through wise design and material choices. We can create efficient buildings with low energy use, which can be supplied from the renewable energy sources. And we really need to change the way we think about energy and carbon emissions, so that we can also balance these emissions by the climate positive initiatives, so that the net carbon footprint over the time can be zero. So it's time to take questions from the audience. It looks like we have a lot of questions. So our first question is from Prachi. Are there any open sources tool for LCA?
Are there any open sources tools? I'm not sure if there are open source, and by open source, I am assuming you mean free tools. I think the databases have like some sort of subscription that is needed, but there are a lot of data sources out there. I would say that it's really important to vet the source of the data. So if you are serious about sort of informing your building design with this kind of information, I would say that please do subscribe to the right resources, even if they are paid. And usually the subscription fee is you can sort of like configure it to your needs. But getting that data right is is quite critical. But I'm sorry, I don't know if there are like completely free resources out there.
Okay. The second question is, are there any project with fuel cell microgrid in US?
With fuel cell microgrid. So fuel cells is like an interesting thing. So let me like break down this question a little bit. Microgrids, yes, I think, and a few years ago, I think everyone was like talking about microgrids all the time. There are a few projects that are complete microgrids that even we've been a part of. I think resiliency, honestly, is like one of the major drivers when you care about your having like a separate network for your building or for your campus. I think that's where we see a lot of interest in microgrids. Oftentimes, if campuses have multiple energy sources and they see an opportunity to sort of like balance them out, that's when we see microgrids being applied. So yes, I think there are quite a few microgrid projects. Also, if it is a completely islanded type of a situation where there is no electricity connection, those tend to have microgrids. Fuel cells, I'm not sure if you meant hydrogen fuel cells, but if you did, then hydrogen fuel cells, I haven't seen an actual project quite yet. Will be very happy to see one. But natural gas fuel cells are everywhere, and they were used or still get used sometimes for cost savings. And they are a very popular technology, and they are everywhere. But not, I mean, energy storage is great. Having access to energy storage is great, but if the idea is to reduce carbon emissions, just having a natural gas fuel cell is not probably going to solve the issue.
Okay. So the next question is, please can you elaborate on the embedded carbon of materials?
Okay, I'm not sure what that exactly means. Can I elaborate? Basically, embodied carbon of materials is the carbon associated with the extraction, manufacturing, assembly, transportation, use, and then the life. So rather than thinking of a material as a product that you buy and put into your buildings and you only care about that life of that product, it is caring for and basically calculating the impact of the product for its entire life, and then not just looking at it on a product by product basis, but instead taking all those products together, putting it in a calculator and finding out what the overall impact is so that you know what the drivers are. So you might know that your concrete and your steel in your building is like the worst, they are the worst offenders, and everything else is maybe under control, or you can like or if there are only a few opportunities, you know where to focus on. So that process of figuring out where the carbon goes within the materials, and then coming up with strategies to reduce carbon emissions of individual materials to have a better impact on the entire project is called life cycle analysis. I hope that answers your question.
Okay, the next question is, do we have easy access to the data sets required for the LCA for every region, or it is just a comparison using global data sets?
No, excellent question, and very, very important to have regional databases. So we find it, and this is a rapidly evolving field. So it's not that we have access to everything here in the US as well. So it is extremely important to have regional knowledge and regional databases. So if you use global numbers, it's going to like skew everything so radically that it's like completely worthless, because and just like if you try and understand why that is the case, is because at the end of the day you are capturing the energy associated with the process of making a material, and the energy is going to be different from one place to the other. So you can't really use global numbers. That is going to skew your entire calculation. And I mean, it's a perfectly fine academic exercise, but if you're doing this on a live project, I would highly encourage you to use your regional database or try and work with your manufacturer to come up with one.
Next question is, what would be the construction cost between a carbon neutral building and a traditional building?
Excellent question again. And I don't think there's like a set dollar value associated with this. So, and I think if you remember like some of the example or some of the projects that I showed at the very beginning, it depends on what you're trying to do, right? If you're building a house, that you're trying to make carbon neutral, I don't think there is any cost add. It's wise decisions. It is smart design. It is maybe a little bit more soft cost that the designers have to put into. But I don't think it is like increase in construction cost, especially in India. I feel like, you know, there's access to such fabulous materials and really low energy materials already, and so a lot of know-how. So I don't believe that would be an additional cost. As you enter into the realm of complex buildings, let's say you're building a lab and or a hospital, and that's where you want to achieve carbon neutrality. I think in those cases, those are complex buildings, and those might require additional layers of security, of resiliency that you may have to factor in. So those might, have a higher cost. But again, if the focus is on the fundamentals, which is how do we make the architecture right, how do we make those smart decisions in the beginning, and then focus on material selection, etc. I don't believe it is like a exponential cost add. But sorry, I don't have like a number to assign.
Okay. The next question is, can we measure the interaction of the carbon neutral buildings with the occupants' behavior?
Can we measure the interaction?
Hello?
With occupant behavior? I guess yes. I think that is very much possible. Like, so from a feasibility perspective, yes, very easy to do. Just put a bunch of sensors in there. The carbon calculation is pretty straightforward once you again like have some basic information. So yes, I think that can be done, and you can sort of like draw some conclusions around whether people are leaving their equipment on, and whether they need reminders, or whether some systems need to be automated. And whether occupants have an influence on carbons, and I think that.
Okay. The next question is, can we measure or calculate the carbon emissions at every step, covering transport and waste?
Excellent question also. Yes, I would. So welcome to the world of scope 1, 2, and 3 emissions. What we talked about today are mostly scope 1 and 2 emissions. Scope 3 would include the things that you just described, and it can be done, but it is very tough. We've tried to do it on several projects, but it's hard. Like when you're talking about transportation, how are you going to predict what occupants are going to do, what vehicles they're going to use? There are a lot of assumptions that get into it. But again, if you're trying to get like a big ballpark, that if you're looking at embodied emissions, operational emissions, transportation emissions, like how do those compare? And waste emissions, how do those compare? And which one is the biggest offender there? I think for that level of calculation, I think yes, that can be done. There are lots of metrics in the world of transportation emissions also that can be used to create that calculation. So yes, it can be done. It's a little hard to do because it ends up relying on a lot of assumptions, but can be done. And same with waste. I think waste is actually very much quantifiable. and often is tracked on projects.
Okay. The next question is, do we have any kind of software that can be connected to the building electronically to get a suitable sustainability report where we can see the data and take a conscious attempt to reduce carbon footprint?
Yes, there are the controller that I mentioned in the California College of Arts project. There are many products, and at the end of the day, it is a control logic that needs to be written. So it is a piece of code that needs to be written, and yes, that can be done. And it is very controllable. So yes, very much can be done. And then again, for the Indian scenario here, at least right now, if you think about it, right now in the grid, you have about like less than just close to 20% renewable energy um, penetration. So essentially, if you look at your fuel mix, it is not going to, your carbon emissions profile is not going to vary significantly. I think it is going to happen in the next decade and beyond. So for the buildings that you're building, I think it is going to happen. But for the existing buildings right now, it is pretty flat. So you can do that calculation and inform occupants and influence behavior as a result.
Okay. So we have many more questions, but we'll take a few more, one or two.
Okay, sure.
The question is, what is the payback period of a net zero building?
Oh, okay. What is a payback period for a net zero building? So I have designed net zero buildings, net zero energy buildings that have a payback period of less than 10 years. I have also designed net zero energy buildings that have a payback period of more than 30 years. It depends. I don't think there is one answer, unfortunately, for that.
Okay. So thank you, Shruti.
Yeah, of course.
For giving us an insightful presentation on the topic future of carbon design.
Yeah,
and it was a pleasure to have you with us.
Absolutely. Thank you very much for inviting me. This was fun. I am very happy to be presenting to an Indian audience. So thank you for having me, and happy to answer any other questions too. Feel free to reach out to me if you have any questions, or if you have more to talk about.
With that, we have come to the end of the webinar today. I hope you enjoyed today's session. We appreciate you being here, and I will see you in the next one. Till then, stay safe, stay indoors. Thank you.
Thanks, everyone. Good day now.